This is a video that serves as an introduction for chapter 22, which is all about Gauss's law and calculating electric fields. So in chapter 21, you learn that electric charge is the source of all electric fields. So if you have a charge, it produces a field. That is always the source for electric fields as far as you're concerned thus far. Now, what the flux means, it's simply the number of electric field lines that go through an area. Okay, so you can think of electric fields and electric field lines as the density of lines is the field and the actual number of lines is the flux. So basically, you can sort of demonstrate it here. So that the flux here would be three lines. So the electric flux is 3. If they go perpendicular right through a surface like that, then this is the area, this is the field. Then the definition of the electric flux is you take the strength of the field, which is the density of lines, so that's the lines per area, you dot it with the area vector. Now it's real important that you understand area vectors. So this is an area vector. The way you represent an area with a vector is a normal vector. So the area vector is always perpendicular to the surface, and it has the value that equals the surface. So say this area was 3 meters squared, and we had an x, y, z like this, and I, j, k. Then we would write the area vector is 3k hat. Okay, so 3 meters squared is the magnitude and k hat is the direction. You can have a curvy surface, like a sphere, and then you can have just a little bit of area. We would call that a dA, a little bit of area vector, perpendicular to the surface of the sphere and always pointing out of closed surfaces. Now this sheet of paper over here, well, the area vector could point down. It doesn't really matter, but it just has to be perpendicular to this surface. Okay, so the flux can change depending on the orientation of the surface compared to the field. So the PowerPoint slides that you looked at are quite good in this respect. So what they're trying to get at is if you have a field that goes to the right, like this, you're going to have maximum flux if you put your surface like that. But if you put your surface like this, well, those field lines aren't going to go through at all. And so the flux here would be 0 because they skim over the surface. They have to pierce through in order to count. So the flux here would be 1, 2, 3, 4, 5. This would be 5. And then at any given angle, like so, say we put our surface, it's a little tricky to draw these surfaces, at some kind of angle like this, where the field is like this. It's this angle between A and E that goes into the definition for the dot product. So it's E dot A. So it depends on the cosine of the angle. Okay, so that's the definition of flux. Now what this chapter is all about is Gauss's law. It is a law that you're going to use to calculate electric fields. So once again, we're carrying on like we did in chapter 21. We want to calculate electric fields. That's what it's all about. The fields. Now, you did the rod, the ring, the disk, and you realize that it's a big, long integral in order to do that. We are not going to do the rod, the ring, the disk in this chapter because it does not work for the way we're going to use Gauss's law. So in order for us to use Gauss's law, it's like this, E dot dA is Q in over epsilon naught. In the textbook, they call it Q enclosed, but this in means inside a Gaussian surface. And I do a whole bunch of examples of how to apply this, but basically this integral can apply to any electric field in any region of space. However, it can be a very messy integral. And what this circle means, this means closed surface. So it means you have to have a box or a sphere or a balloon or some kind of closed surface, and Q in is the charge inside that surface. Now what we do is we reduce this to extremely simple terms on the left here because we're going to do super symmetric situations. We're only going to do infinitely long rods, which are super highly symmetric, which makes that integral super easy. Or we'll do spherical charge distributions, so perfect spheres, or we'll do infinite sheets. And you'll understand why it has to be infinite. It's because we don't want any edge effects. We don't want any funny direction of electric field. We want everything to be beautifully symmetric and just straight out of this field, out of this area, like this. No edge effects. It's an infinite sheet. The rod, now you might say, well, we already did the rod, but remember, this is an infinitely long rod. So this rod only has a field that goes like this. There are no edge effects. Okay, if you want to do a finite rod, you have to do that integral you did in chapter 21. Spherical symmetry is fine. The field is going to go out like this. And we'll do spheres that are solid. We'll do them that are hollow. We'll do them with uniform charge density and non-uniform charge density. So you'll be looking at a whole bunch more videos on how to do all those calculations a little bit later. Okay, so that should be it.